Hello, my name is Kasper Aagaard Mortensen, and I have the pleasure of presenting our work Marigold for efficient k-means clustering in high dimensions. This project is a joint adventure between the computer science department and the physics department at Aarhus University in Denmark. As it turns out, the physicists have a lot of interesting data where clustering in high dimensions is very applicable. When discussing clustering, Lloyd's algorithm often should come into play, as it is the most basic way to describe the problem, and also it's the one a lot of people know, so it often appears hidden in a lot of tasks. So to describe it shortly, we have a lot of data points, and if we compute the distance between these data points to some number of centroids that describe the potential middle of a clustering, we can basically assign all the data points to the closest centroid and keep updating until we converge at some clustering. So in general, the complexity of Lloyd's algorithm would be described as a linear complexity between the number of centroids and the data points, as we have to compute all the distances. But what we sometimes forget is that we also have to consider the actual data dimensions, because if we are computing in some very high dimensional space that goes well beyond the number of actual data points we have, this is very important to consider in the actual runtime. So in high dimensions, Lloyd can often be expected to be very slow, because we have to compute all the distances over all the dimensions, and this is the problem that we address. So it turns out that the physics department, they have a lot of cool machines that can do all sorts of things, but the main point for us is that they produce data in very high dimensions, which, for example, can be expressed through some spectra, which is basically images, and a nice image have a lot of pixels, and if we are considering the pixels different dimensions, we of course have a lot of dimension to take into consideration if we want to cluster these images. So here are some different examples of how such images could be. We have some light spectra of shooting light onto some material and measuring how we get some electrons returned from that. But it could also just be like a general image of the sky in a very high dimension, where even when we zoom into each individual object in the sky, we still have very high dimensional images. It turns out it's not unheard that if we compress all of this data before trying to do something with it, for example clustering, discoveries can be lost, because it's very important that we include all the minute differences when we want to compare all of these data. As seen in the top right, the differences between these images can be very minute, and if we, for example, try to first do some dimensionality reduction to speed up a clustering process, these differences can be completely lost, and hence discoveries as well. This makes it very important from the physicist's point of view that the clustering we do is exact, in the sense that it will produce the exact Lloyd's results that considers all the dimensions of the given data. So let's consider some available options we already have for fast k-means clustering. First of all, dimensionality reduction, but the problem here is that it will cause the resulting clusters to be approximate results, which is not what we want. We want the exact results of Lloyd algorithm. And there's also some practical issues that often, to maintain any reasonable guarantees, we have to do the dimensionality reduction still on high dimensionality of the data. Otherwise the approximations may simply not be good enough. And also often these approaches are based on already having some approximate clustering to work from, which in practice often is just simply running Lloyd's algorithm for a few iterations first to get some initial approximation and then use that. So in the end, we have to use Lloyd algorithm anyway. Another approach is distance bounding, where we can get the exact results. This is often done with the triangle inequality to basically set some bounds for whether or not we are close to a given cluster centroid, such that we can ignore all other centroids. Due to the curse of dimensionality, this becomes less effective in high dimensions, but we will get the exact results which we are looking for. And of course, there's the side note that if these bounds are not good enough, then we will basically default to Lloyd's algorithm anyway, because there's nothing to gain from them. So here's a goal. We want to merge these two approaches so that we can get the speed of both of them while maintaining the exact results. And this is not just a goal, this is what Marigold does. So, and we will see that later. So let's start with k-means using the bounds. To use the bounds and the triangle inequality, we basically pay an upfront cost of calculating centroid to centroid distances. What this allows us to do is to prune point to centroid distances instead, using the triangle inequality, where we can basically define some subspace around any centroid, where if any data point is within this, we are guaranteed that there are no other centroids close enough such that that data point should belong to another cluster. Using bounds, we found an opportunity to combine two existing methods, Elkan's algorithm and Hämmerle's algorithm, which both rely on exact bounds using the triangle inequality. There are other bounding methods that use approximate bounds, but again we want the exact results, so we are using methods with exact bounds. The main difference is that Hämmerle is uses a more loose defined lower bound, but potentially is a lot faster if that bound holds, where Elkan is using a lot more fine-tuned bounds at a cost of a higher memory, of course, as there are more bounds to keep track of. And as we can see in a high dimensional space, there's a huge difference between these methods, and even Hämmerle can sometimes be slower than Lloyd due to the upfront cost of computing all the centroid to centroid distances. The main takeaway here is that we have three bounds that we want. We have a lower bound from Elkan's method that bounds the distance from a point to a centroid. We have an upper bound from Elkan's method, where we are basically upper bounding the distance to the centroid that a point is assigned to currently. And then we have a lower bound from Hämmerle's method that bounds the distance to all other centroids that a point is not assigned to. So, how does it work? First, we prune with Hämmerle's method, where we have a lower bound that bounds the distance to everything we're not assigned to, or the point is not assigned to. So in this case, if x is assigned to centroid 1, then we have a lower bound to all the others. That means if our upper bound from the Elkan's method is lower than the lower bound, then we know that everything else that we could potentially assign the point to is further away, and hence we don't have to do anything more for that point. Another case could be that the lower bound from Hämmerle's method is below the upper bound from the Elkan's method, and if that is the case, then the current assignment may be wrong and we have to investigate further. So first of all, we calculate, if so, the exact distance to what we're currently assigned to. Hence we are doing one full distance calculation. And then we skip away from using the Hämmerle's lower bound to using all the Elkan lower bounds instead. So now we have to compare the distance or potential distances between the centroids to the point, instead of just doing them all at once with the lower L bound. So we compare to the first one, which we're currently assigned to, which we can't really do anything about yet. But if we're not changing our current assignment, then that means that we should be assigned to this one anyway, so we just keep it for now. Then we can check for the second centroid, where you can see that the upper bound is below the centroid's lower bound, hence we are not assigning to that one. Finally, we can compare to the last centroid, centroid 3, where we can see that the upper bound is now lower than the lower bound for the distance to a centroid free. Hence we have to investigate further. So we calculate the full distance, and then we update the lower bound and check again if it is still lower, and if it's still lower, then we assign to that one instead. In reality, a lot of more calculations are going on behind the scenes to make everything work, and we can also utilize those, but the main takeaway is that by combining Hammerly and Elkin's method, we can do some coarse pruning first, using Hammerly's method to potentially gain a lot of speed by not having to do detailed calculations. If that is not good enough, we can switch to Elkin to still have a benefit over full distance calculations. So here in this plot, the triangle-based k-means approach, the fastest one, is the combination of using Elkin and Hammerly bounds. So the reason it is faster is mainly that the payment of a centroid to centroid distance calculations is already done with Elkin's method as well. So when we're using the Hammerly bounds, we're basically getting that extra performance of sometimes being able to skip a lot of calculations for free, where if we just used Hammerly alone, the centroid to centroid calculation is not worth it, as we are not gaining enough speed from doing Hammerly pruning alone. But all of that was just using the triangle bounds, so we can do more. We can combine it with stepwise distance calculations, which is a technique that comes from India's neighbor search, which it shouldn't be too surprising that we can apply that to k-means clustering as well, as we are basically looking for things that are nearest neighbors, in this case a point to the nearest centroid. The way it works is that we are basically calculating an exact distance on a fewer dimensions, and then bounding the distance using the rest of the dimensions. Hence we only have to do a little distance calculation and utilizing the bounds instead to make a speed up. This works really well if we first compress the data using some transformation that preserves distance between two data points, as by doing so we can compute the almost exact distance using fewer of the dimensions, and then use the bounding on the rest, which means we still get very precise bounds. The quick description of how we do this is that we can bound the squared distance, where basically by calculating a small bit and maintaining the bound on the rest, we can get a lower bound and upper bound on the squared distance. And if that is not good enough, we can just expand the exact calculation a bit and keep going if needed until we know the full distance. The good thing about this is that we can pre-compute all sums in these bounds, as each sum is only over either the data or the centroids. So for the data we can compute it once beforehand, and for the centroids we can compute the sums for each iteration. And then stepwise we can prune like we did with the older bound methods by comparing the upper bound and lower bound. And if the upper bound is lower, then we know that everything else is further away. Now the main contribution of Marigold is that you can merge all these approaches by merging the stepwise bounds with the triangle bounds to basically avoid doing the full distance calculations. And our experiments result shows that this merge works very well in practice, as we can utilize both the stepwise approach and the triangle bounds approach at once. And yes, the plot here shows that Marigold in general performs best in high dimensions, and even if we include a bit of dimensionality reduction, Marigold will still be better to some point. Hence it also will work for if you can accept a little approximation in your results. And if you're looking for more details, feel free to send me an email, or you can also look at the code, which we'll link to here. Have fun.